sleepy. Coffee. There's a nice coffee shop just around the corner if you don't know. So I just stopped by there. Good. So, any questions on the material that we've covered so far? No? You guys are ready to solve some hard problems? Yeah? Okay. So let's do a review of what we've covered. So, I guess at a high level yesterday, what we introduced was this sequence data structure. And obviously, this is one of the fundamental data structures, right? It can be thought as a replacement of lists in sequential programming. So effectively, lists, but a sequence is effectively a list, but parallel. Furthermore, right, so let's see, we talked about some fundamental operations like length of a list, indexing into a list, into a sequence. We talked about tabulate, which allows us to make sequences, right, by iterating over an index and mapping the index to a value. We talked about then from tabulate, so you can think of this as a constructor. From tabulate, we implemented map, append, and similar operations that allow us to basically, map allows us to map a sequence into another one, append allows us to construct bigger sequences. And now we talked about a set of operations for augmenting, aggregating, I should say. Not augmenting is not the right word. Aggregating over sequences. For example, we talked about initial iterate. The advantage of iterate is that its work and span, right, were the same. So it's completely sequential, which is not a good property, which is not something that we would like. We would like to have log n span. So then we talked about reduce, which gave us order n work and order log n span. And what was the assumption that we made for reduce? Do you all remember? Associativity. So that's very important. For reduce, the helper function has to be associative. So reduce is not as powerful as iterate because it's not able to take advantage of the history. But when you don't need that history, it is a good replacement. And sometimes we talked about, well, sometimes you do need that history. And for that, we talked about the scan operation. And then we showed you an implementation technique. We didn't actually detail the implementation. But if you wish, you can implement scan in one afternoon, right? So when I first learned about scan, the first thing I did was I went home, I sat on my computer, I set up my desk, and then implemented scan in one afternoon. That's all it takes. Maybe 2 hours, maybe 3 hours. That was in ML, by the way. So you can implement scan in 2-3 hours. It requires linear work, logarithmic span, which is great because you see, you basically get a lot of the power of iterate in logarithmic span. So that's the key point. And obviously, all of these operations, like maps, tabulates, appends, these are all order 1 span. They are incredibly parallel. Okay, so basically, what we see is that for a pure data structure such as sequences, all of the key operations that you can imagine performing on them can be done in parallel with no fundamental difficulties. And when it comes to updates, things are a bit more complicated. We talked about an update operation right, which requires order n work and order 1 span. This is quite inefficient, basically because it copies the sequence. And then we talked about inject. Okay, inject is more like a bulk update. It performs multiple updates at a time, and it does order m plus m work and order log m span. Okay, so that is a lot better. Specifically, if you're performing as many updates as the number of elements, then inject makes sure that your updates are effectively constant time. And we talked about how this is important because in a parallel algorithm, you often do multiple things at a time. So if you're performing updates one by one, chances are that your parallel algorithm is not a good one anyway. So this comes in handy, right? So this comes up in many cases. And in fact, we implemented filter by using tabulate and inject in order n span, in order n work and order log n span. Okay, so in summary, right, this is a very nice picture in the sense that you can do these bulk operations, you can operate on sequences in excellent work efficient fashion and in parallel. Any questions on these operations? Anything that you might have questions? Good. So because of the associativity, right, scan also assumes associativity, by the way, it can require a bit of thought to come up with the right helper function. So when you're using these, the key, usually difficulty or challenge, which is not necessarily a huge challenge, but it sort of starts getting used to a little bit. When you, for example, throw in a helper function to iterate, you don't think about its associativity because you don't have to. But when you're doing reduces and scans, you do need the operation to be associative because otherwise it won't be correct. It would run, but it won't give you the result that you expect. So that requires a little bit of thinking sometimes. You have to think, oh, is this function associative? And how do you prove associativity, right? It's not usually too hard, right? So if you have your function f, helper function is f, you basically have to prove that this is equal to f of x comma f of yz, right? So in other words, an example is if your function is plus, you prove that this parenthesization is the same as that parenthesization. And that can require, considering a few cases, but it's just straightforward case analysis pretty much. Okay, questions? Good. Now, so what we thought in this lecture would be cool is to put these tools that we've learned into use by considering a classic problem. And then we'll try to solve this problem in just multiple ways by using these techniques that we've learned, and then consider its work and span, consider the efficiency and parallelism, basically. Okay, this problem that we're going to consider is called maximum contiguous subsequence sum problem. Okay, short for MCSS. Long for MCSS. This is a pretty cool problem. It was initially introduced by around 1979 by a Swedish statistician, actually, who used to teach in Brown. And has attracted the attention of computer scientists and has been solved pretty much a few years after it was proposed. It's a reasonably simple problem, but it wasn't immediately clear, for example, to people who first started working on it how to solve it. So it requires a bit of thinking. So what's the problem? The problem is you're given a sequence, like this, let's say. Okay? And you're asked to find a contiguous subsequence. A contiguous subsequence is a chunk of this, a segment of the sequence. Like that one would be a contiguous subsequence, right? That one would be another contiguous subsequence, so would that one be? And you want to find the one that has maximum sum. Okay? For example, for the sequence, what would be the maximum contiguous? What's the MCSS? 534, right? Good. So that looks like you guys got the right one. So this is like 12.
Would you give the larger sum taking from the start? Yeah. 1 and 2 is greater than -1.
Oh, excellent. Actually, you're right. Yeah, so that there's a better one here, yeah. No, it's not very easy, huh? So it's like, is it 14? Yeah, okay, excellent. So that gives us a better sum. Good, so he was introduced by a Swedish statistician. He wanted to understand some segmentation properties, and he thought that this was a good model for that problem. And then he mentioned this problem to Shamos, who used to be a department head in computer science at Carnegie Mellon, Michael Shamos. And he mentioned the problem to Bentley. Bentley is a pretty well-known algorithms researcher. He also used to be a faculty member at Carnegie Mellon. And Shamos devised a divide and conquer solution. But his solution was not work efficient, it turned out. His solution was order, I think, n log n. Of course, they're only working in the sequential domain. And obviously, right, what's the lower bound for this problem? How much work do you have to do? At least linear, right? So you would need to do at least linear. And it would be nice to match that lower bound. So linear work seems possible. In terms of span, any ideas how much span this would take? Can we do it in constant span, for example? No, right? Why is that? Because at least we have to add some things up. We have to aggregate things. So intuitively speaking, it seems like we would need this much span. Right, so and that would be our goal, to match that. So Shamos' solution actually wasn't work optimal. And Bentley and Shamos kind of talked together for a while, apparently, and then they decided this is the best you can do. And then I think Shamos then gave a talk on the problem at Carnegie Mellon in a statistics department meeting. And a statistician there, Jay is still around, so I see him, but I can't remember his last name. What's his last name? I have it on my notes. Kadane. Jay Kadane solved the problem on the spot during the talk and gave the first linear work algorithm for the problem. So that's an interesting story. This is all happening in 1980s. So that's the story of the problem, right? Good. So what's sort of the first, right, brute force method? Let's think of the brute force algorithm that you can think of, right, just to warm up, to solve this problem. What can we do? Absolutely, we can look at all the possible subsequences, right? And then try it out. Let's write that algorithm actually just for fun. Okay, so what I'm going to write these algorithms, I'm going to introduce just a little bit of syntax. Okay, so let's write a brute force solution. Suppose I'm given the sequence A of numbers such that. So what I want to do is, I want to create a sequence of all subsequences. Okay, so we can do that by tabulate, right? So I'm going to use this syntax, sequence comprehension syntax. Okay, I'm going to say for ij between 0 and length of A, okay, consider all subsequences. Let's more precise here. Okay, so that's a sequence comprehension syntax. What this is saying is tabulate over I, tabulate over J, and for each I and for J, construct all subsequences. Does that syntax make sense? Right? That's all we're going to use in this lecture in general, pretty much. So that's a tabulate. So we've constructed it all. So now what do? We want to pick the one that has the largest sum. How can we do that? Any ideas? Reduce. Good. So let's first do a reduce to compute the sums. So we can do a reduce with a sum operation. Okay. I'm going to write quote unquote, but you know what I mean here. What you want to write here is actually lambda x and y, right? X plus y. So just to be concise, I'm going to use that. Reduce, actually, sorry. Good. Let's reduce. So I'm going to reduce each one of these guys, okay? Okay, so what this does is I'm going to map over my sequence and compute the sum for each one. Is that clear, everybody? Okay, so what this does is that what we get here is a sequence of sequences, right? So what we have here is a sequence of sequences, like this. Okay, these are some numbers. And now what I'm doing is mapping this reduce plus x, reduce plus function on each one. And that gives me the sum of each one. And then I do another reduce to pick the max. Reduce, identity for max is minus infinity, right? Which way did we order things? I think we ordered them, I forget now. Anyway, so minus infinity max b, okay? So that gives us the maximum contiguous subsequence. C, excellent, thank you. Yeah. That's the brute force algorithm. So let's analyze the cost. The cost really is in this tabulate. Why? Because we consider all ij's. There are n square of them. And for each one we do a subsequence. That's a constant work and span. So constructing this whole thing is order n square work. And order 1 span. Because tabulates are constant span. And then we do this map over n square different sequences, each one of which could be as large as n. So this guy here takes order n work, and there are order n square different things in here. So the total work here is order n cube. And because of this reduce, order log n span. And this guy here is just going to pick, again, order n square work, because there are n square different sums, log n span. So it's dominated by this reduction here, giving us n cube work and log n span. Pretty terrible algorithm, right? As you would expect. That's what you get for brute force. Questions? Okay, very good. So that's just a warm up, right? We're not going to use that algorithm, but to warm up. Okay, Now, why is this algorithm so inefficient? Right? Because, any ideas? Sorry? All possible subsequences. Can we do something better? We should be able to, right? Because it's not taking advantage of the overlaps between sequences. Basically, what this is doing is, so if you have two subsequences like this, right? Let's say that you have this subsequence and this subsequence. Well, the sum between these two guys differ by just one element. And it's not taking advantage of that. It's computing everything from scratch. Okay? So let's try to take advantage of that. And we want to do that by we're going to do this in baby steps. So we're going to define now a version of the problem that says find the maximum contiguous subsequence sum that starts at a given index. Okay? So let's consider a modification of that problem. Let's call that MCSS begin. Okay? Where this says it's exactly like that problem, but we are interested in finding the maximum of subsequences that start at a given index. Okay? Consider all subsequences that start at a given index and find the one that is maximal. Okay, so now I want you to work on this little problem. Pair up with your friends next, your neighbors, 2 or 3 of you guys, and then try to come up with an algorithm for this problem using the primitives that you've seen. Okay, that does linear work, and it's also parallel. Ideally, order log n span or order 1 span or something like that. Is the problem clear though to everybody? What we want to do? We want to find the maximum contiguous subsequence subproblem starting at a particular, only for subsequences starting at a particular index.
always exponential. There is no need to ignore that. So what's the particular f of I is less than 2, then it's negative. Then it's max
Okay, any ideas? Who solved it? Linear work, Lagrange span. Do we have linear work, Lagrange span solutions? It's just one. You guys have one as well? No? And you have one there. Do you guys want to tell us what your solution is? Yeah?
So what you do is you just scan over the subsequence starting with I and going to the length of A minus 1 with an add, and then you just reduce with a max over that.
Okay, excellent. That's a very good solution. So let me write. Okay. So MCSS underscore B, a sequence A. So I think what they first, and then we want to take an index I. This is where we start. So what your friends do is I think they first take this I dot dot A minus 1. Okay, so take the relevant subsequence. And then they do a scan, plus scan, over B. What's the identity for plus? 0, right? That's it. And then they do a reduce with max. Identity is minus infinity, C. That's it. Okay? So pictorially what they've done is, so they've taken the sequence. We wanted to find all of the contiguous subsequences. It's basically a brute force way, but it's a smart brute force in the sense that they're starting at I, and then they're using scan to compute the sum for all contiguous subsequences, right? And then they're taking max over those. Is it clear? Solution? Right? So what's the work? The work is the scan is going to give us order n, and order log n span. And the reduce is going to give us order n order log n. So we got it. Okay? There's something slightly wrong with this algorithm. Slightly, not like fundamentally or anything. There's an edge case that they didn't consider. Negative?
If like the sum is negative, because you have to consider the empty sums.
Oh yeah, that's okay. Scan, remember scan does that. So scan does that, but it's very similar. It's a very similar problem. Recall, what did scan return, if you remember? What did scan return? It returned all of these guys, total sum, if you recall, right? Scan is a little bit funny in the sense that it starts with the empty sequence. The first element of the result is the empty sequence. The second element is the singleton sequence, so on, all the way to n minus 1, and then it returns the total sum as a, sorry, not here. Returns the total sum as a separate value. Like, let's call that S, like this. So it returns the total sum, and then obviously the whole subsequence could be all of the subsequence could be all of the sequence itself. So we have to, when we're doing the reduce, we also want to consider that. So what we want to do is, let's say D is append the value C into S. There are multiple ways you can do it, but anyway, so perhaps the easiest way to do it is to take the max of this along with S, so that we consider the possibility that all of the sequence is actually the maximal subsequence. Okay, it's a small edge case, not a big deal. Okay, good. So now with this solution, what we've taken advantage of is we've taken advantage of the fact that these subsequences all overlap, and we don't have to recompute them one by one, so we've reduced it to linear log n. Okay. Now that we've got this nice algorithm that's actually efficient for a single start position, can we solve our original problem by reduction to this? Our original problem required finding the heaviest subsequence, largest subsequence across all. Right? What can we do? Someone said something. Said I to be 0? That's a good starting point. Setting I to be 0 would only give us the largest subsequences starting at I0. But not all possibilities, but just those starting at I0. So building on that thought, what can we do? Map it over all of them, right? So what we want to do is consider all subsequences by considering all start positions. So what we do is, now let's solve this problem by reduction to this. Sequence A, okay? So what we want to do is we want to construct the sequence B. Do we need to? We just need to map, right? We don't need to do anything. So let's call, we want to do is we want to call MCSSB on all i's. Okay, and then we want to take, let's call that sequence B is going to be, we want a sequence for all I, so, I see. All we need is a tabulate, okay? For each starting position, that's a tabulate that says for each starting position, call this function. And that's going to give me a sequence, and I'm going to take the max of that. Okay, that's my algorithm. Is this clear what this is doing? It's just a tabulate, right? If I have to write in our function, we would do this. Tabulate, lambda I calls MCSSB AI, and then length of A. That's translation of that function. Just syntactic sugar. And then we do a reduce max. Okay, so we know that this is order n work, order log n span, this particular function, but we do that n times, so it's order n square work, and span is each one of these is order log n. We take the max of them, so order log n span, because all of those could be done in parallel. So span remains order log n. This is order log n order n square, so in the end we have order n square work, or log n span. Okay, we've improved our algorithm from n cubed to n square by using this technique. Any questions? Okay, very good. So now, okay, we're going to do another twist. We consider the start. Let's consider the dual. Let's do the same, but for the problem of finding the largest subsequence, what was it? Largest what's the word? Contiguous, largest contiguous subsequence. Contiguous subsequence, yeah. That ends at a particular position, okay? So we're going to define this problem MCSS underscore E, right? Which basically says, okay, find me the largest subsequence that ends at a particular position. So the problem takes the sequence and a position I, and it says, find the largest one that ends, okay? So now you probably just thought, okay, reverse scan, right? No, okay. So we don't want to reverse because, yes, you can solve that problem by reversing and scanning, but we want something slightly different because we're going to combine these two guys to solve our original problem, right? So what we want to do is, what I want you to come up with now is an algorithm that does this without reversing, okay? Slightly harder than the other one, but not too much harder. So pair up again. If you don't have a friend, go find one, right? So you didn't come here to sit alone. So go find a friend and work on this problem. Is the problem clear? You solved it already? Somebody solved it? Someone solved it already? You said, no, okay, sorry, yeah.
What if you multiply by negative and then apply the previous one?
Negative. Never mind? Yeah, okay. Yeah.
Can we do a perfect sum over it and find the subsequence, then we reduce it with subtraction?
Subtraction. You're okay. You're getting there. Okay, good. No, but you might be ahead of me. Very good. That's a good idea. Yeah. I'm sorry?
That tabulate right there, where does that fit in?
That's a translation of the syntactic sugar. So I have the syntactic sugar.
Okay, right,
Yeah, so it's just, yeah. Order and work? That's too high span, that's sequential. See if you can get log n span. Think about scan.
The divide and conquer is in n log n. Why isn't it like linear?
It can be done linear. That was the algorithm that Shamos came up with.
Yeah,
But it can be done linear, yeah.
but
We will see how to do it in linear work.
Okay.
Yeah, we'll see that.
yeah, okay.
Yeah, we'll see it. Yeah. Okay, I was gone. Any solutions? Raise your hands. Who solved the problem? Solutions? Somewhat. Are you still working? Do you need more time? You want more time? A bit more time? Okay, you have it. Yeah.
That's taking S minus CG.
So basically, in your network was somehow find a way to scan that network to reduce the what could be still network? What's the cost of doing all of these? I mean, what's the span of for all i's, for all threes, we will take all i's less than 3 and subtract it.
Minus maybe then we get some list there, and then we just take reduce max over that list, and then we kind of this give us the zero case from the scan is the
Okay, let's queue up at this point. Anyone who's had some ideas? It doesn't have to be complete. You can tell us your ideas. Yeah, go ahead. Reversing is not allowed. Good. I did say that, right? I did. Sorry. Distracted driving. Okay. Yeah.
So we scan with plus over the sequence.
Okay.
And then we take that last element, which should be the sum of the whole thing, and we map that number minus each element.
Cool.
And that should give us the it'll like the rightmost thing would be nothing, and then the leftmost thing would be.
Okay, that's a good solution. I like that.
And then we take the max over that.
Max over that. Okay, very good. So, observation, right? Your friend made a very good observation. He says, okay, look at any sequence. Consider a sequence and consider a subsequence. Okay, like this. Now let's call this subsequence B. Now the sum of that subsequence can be computed in terms of this subsequence and this subsequence, right? B is C minus D. All right? The weight of the total value, the sum of the elements of B is sum of the elements of C minus sum of the elements of D. Okay, that's excellent. Now, this means what? This means that if you want to find the largest subsequence that ends here, what we want to find is the minimum subsequences such as D that starts at the beginning. If we pick the min and then we subtract it out, that gives us the max. I'm just rephrasing our approach slightly, it's the same thing. Right, so we have many of these guys, many possibilities of these. Of the D's, we pick the min, and then let's say that the min is this, that gives us the best subsequence. Very clever. Congratulations, your name?
Lucas.
Lucas, awesome. Who's come up with the same idea? I think you did. You did. Awesome, guys. Great. Good, so let's write the code for this. It's very simple, right? Erase that. Write the code for it. So that's an MCSSE problem. Okay, and then we want to take the particular position. So what we first want to do is extract our sequence, 0 to I, that we are interested in. And then what we're going to do is do a scan plus 0 over B. That's going to give us all the prefix sums. Oh, sorry, that's like C comma V, C comma S, let's say, for the sum. Okay, just for simplicity, let's not worry about the empty sequence, okay? It's kind of pesky. The possibility of the empty subsequence being the largest is a pesky problem. So let's define that to be minus infinity, so it's never bothers us. So we get that. So we have the scan sequence and the sum. Good. So then what we're going to do is we're going to take the min over C by doing a reduction. Reduce min plus infinity over C. Now, this is going to give us the minimum prefix. Okay? So our result, therefore, by the reasoning there, is sum minus M. Okay, we take the sum of the subsequence, the complete thing, and then subtract out the minimum prefix, and we got the largest contiguous subsequence ending at that position. So this is a linear work algorithm, right? All of these are linear cost computations. These guys are log span computations. These are all constant. So we have n work linear log n span. Again, very good. Okay. Now we're going to take a little bit of somewhat of a big step, and then go from there directly to a solution that builds on that idea for the whole problem. Okay, so let's see, how can we do it? So the claim is that we can generalize. So in this particular solution, we considered only one ending position, right? But the observation is that we've actually done the work to solve this problem at all ending positions already. Almost. Okay, we're like very close to being able to solve this problem for all ending positions. If we can do that, we can solve our original problem by picking the max over all of those, right? So the only thing that's left is going from here to a place, to another algorithm where we can solve this same problem for all ending positions at the same time. And I claim that we are very, very, very close. Okay, what is it that we're missing? Consider another one, let's say J, another ending position J. For both I and j, all we need is a scan. So we can do, in a single scan, we can compute all of the prefixes. For both I and j, what we need is the min that come before it. That is also just a scan, isn't it? So we can also use just a scan to do that as well. So this algorithm seems to generalize. So the only slight change that we need to make is instead of a reduction there, we're going to use another scan. Okay, so let me write the algorithm and then we can think about it. So we're going to solve the complete problem now by building on this idea. What we want to do is first do a scan. Plus scan to compute all the prefixes. Okay, this gives us all the prefixes and the sums. Good, so now instead of a single reduction, what we want to do is compute the min over all prefixes. So that's another scan. Okay. B. So let's call that C. Okay, we don't need that, I believe. Okay. So now, all we need is a pointwise, so we generalize that S minus M to a pointwise operation. So what we need is map, it's a tabulate. So what we want to do is, we're going to do BI minus CI for each I between 0 and A, and pick the max. Okay. So let me illustrate what this algorithm does. So we take our sequence, and then we compute the prefix sums. Okay, so that's what this does. Gives us B, that's B. And then this guy, now it does a scan min, which means that for each position, it computes the minimum of those guys that come before it. Okay, so we get another thing, the sequence C, that mirrors that, but such that for each position, okay, let me write it actually here so that we have symmetry. For each position, it computes the min that comes before it. So I'm just going to illustrate that with a simple dot, right? Each bullet for position, for example, let's say 5. This bullet is the min sum that comes before it. And in bulk for all of them in one shot. Then, by generalization of that argument, we just pairwise minus. So this way we're finding this D is largest common subsequence that ends at each position. Okay? So this is the sequence of largest or maximum common subsequence at each position I. Okay, for each I, we have it in there, and then we pick the max. Okay, so it might take a bit of time to digest, right? But let me know if you don't hesitate to ask questions. Yeah. We don't know the indices at all, correct, yeah. But we don't need to because we're just looking for the sum. There's some care that we need to, it's important that things line up because of this operation here. We're paying attention that things line up in the sense that when we're looking at a particular position, let's say here, we know that the value at this position in B is the perfect sum. And in the other sequence C, it is the minimum thing that comes before it. So we can then do our subtraction. So we have that, and we have also the min. So we know that the maximal contiguous subsequence ending at that position is that. Okay. That's the optimal algorithm. It does linear work. You can look at each step, linear work, right? Three passes over the sequence. Each one linear work, log and span. 4 passes, and we're done. Yeah. Pretty amazingly beautiful, I would say.
Is there any derivation of this algorithm that have improved or heuristic or improved constants?
Improve constants. Oh yeah, you can improve constants here. That's a good question. Yeah, so we never think about these things in this context, but yeah, you can improve constants by basically fusing these operations. Yeah, for example, the 2 scans can be fused because they're basically running together. In fact, even all the first 3 can be fused. And also the last. I think all of those could be fused into a single pass because they're just basically doing a single operation. I don't want to write the scan for that, though. It's pretty hairy. Leave it to practitioners. Those guys like to bash us anyway, so might as well do the work. Okay, question? Okay, good. So that's it. So that's the contraction-based algorithm. That's optimal, right? So it's order log n, span, or n work. Okay, beautiful. Now, remember I told you that Shamos originally, Michael Shamos came up with a divide and conquer algorithm. This problem also accepts a divide and conquer solution. So let's see if we can drive that quickly. It's actually much more, it's simpler. It's not as good in span, right, as, it's not as, we're going to see that its span is a little higher, but not dramatically higher. It's log square and span. But it can be done in linear work. So let's drive that. It's at least the basic version is very simple, and then the refinement requires a bit of work. Okay, divide and conquer. So in that algorithm, we just use contraction because scan is basically primarily contraction. We can also give a divide and conquer solution to this problem, right? It's conceptually simpler. So we've got a sequence. What do you think we can do? Chop it up, right? So we divide it into 2 parts. And then solve MCSS on this part and solve MCSS on this part. And let's say that this returns us an MA and this returns us an sub B. So we get 2 results, A and B. Okay, let's call this A and let's call this B, the 2 subsequences. Point is that we can do that in parallel, right? So we divide it, split mid. That's a constant work operation. The 2 recursive calls can be done in parallel. We wait for them to complete, and then we get MA and MB. And then we do what? Okay, which one is the best, right? We check if, MA is greater than MB, then MA, else MB. Okay? Something we're missing here, obviously. Yeah? Right, so because this what if it crosses the cut, yeah? So this, what we've done so far handles the case where if MA is here, let's say MA is completely contained here, MA and MB is going to be completely contained, but what if there was another sequence, maybe like this, that actually crosses the cut? So what we're going to do is, let's say that we have a function called best across that computes that, okay? So we'll also recursively get these two guys, and then let's say, you know, MAB is, let's call this function best across that midpoint, okay, so A and B. So then basically pick the max, right? So we pick the max. So result is return max of MA, MB, comma, M, AB. Okay. Now, let's think about MAB. How can we solve MAB? We've already solved it, I think. You just have to realize that we did. Yeah?
We only solved the starting, so it's not negative.
Beautiful? Yeah? Exactly. So this is, you know, this is ending at that position problem that we solved. This is beginning at that position problem that we solved. And that required linear work log n span, right? So we can do that trivially. So we've already solved this problem. Good. So that's our algorithm. So let's analyze the work in span.
Wait. Can't you just compute the left and the right maximum for the two parts, like in the recursive form?
Like in the?
Can you just compute two more values than MA and MB in the recursive form?
Oh, you could. Yeah, you could. You could do that. Instead of best across, you mean? Yeah, you could do that. We'll get to that one. 1 second. Yeah. So this one, what's the working span of this algorithm? So it splits, that's constant work span, and then it does two recursive calls. So work is 2 work of n over 2 plus best across is linear. This operation is constant, so it's order n. Okay? So span is, because we can do these things in parallel, span over 2 plus all of these other guys are constant. So this gives us a work of n is order n log n, okay, somewhat suboptimal. Span of n is order log n. So it's good, but it does too much work. Okay? Why does it do too much work? Any intuition? Well, because of the best across, right? So the best across is actually taking us linear work. And your friend has a good idea, right? He's saying, why can't you just compute those things recursively? Is that right? That's what you're saying. And that, there's a lot of logic to that and a lot of reason because, look, the algorithm must have, like recursively, already considered a subsequence, already considered that sum. In order to compute the max, it must have looked at that sum, the suffix. And similarly, recursively, it must have looked at that. So we just have to be careful to return those instead of throwing them away. So we're doing redundant work here by forgetting the work that we've done in the past by recomputing the best across. So all we need to do is remember that we've already computed these guys. So this is, in algorithm design, this is called strengthening, right? So we're going to strengthen our problem a little bit and our algorithm to return not just the max, but also those prefixes and suffixes, okay? So let's do that. So we're going to get rid of this. So what we want to do is each MCSS is now going to return max and also prefix and a suffix. That means that, you know, maximum prefix and maximum suffix in that sequence. And this guy is going to return likewise MB, PB, SB. And recursively, okay, what we're going to return is the max. What's the max? It's a max of MA, comma MB, comma PSA plus PB, right? Because we want to, the best across is going to be let me draw it here. So this is going to be SA, this is going to be PB, okay? So we consider best across by summing that up. And now our longest prefix is PA, correct? And longest suffix is SP. Did I get that right? No, I don't think so. Something looks very fishy. Okay, so what we're trying to do is we're trying to strengthen the algorithm so that we don't have to compute best across, right? And we did that by returning from each recursive call this, the maximum and also the largest prefix and largest suffix. So suppose that recursive call returns us those two, but now we have to, now from this recursive call we have to return them. The max is easy, right? It's either on the left, on the right, or the sum of the SA plus PB, which is best across. But what is the PA? Is it, what's the largest prefix? Is it just PA? No, yeah.
Oh, it's the max of either PA or
Good.
the sum of A plus PB.
Excellent, excellent. We need to now, right, so it's the max of PA. It could also be this, right? Let's call it sum of A plus PB. And symmetrically for the suffix, we have a similar thing. The suffix is either PB, SP, or SA plus, oh God, I didn't mess up something. Oh, SA, no, it should be like, let's use another thing. Sigma A for, let's use T, total A. Okay, total of A. SA plus total of B, right? Because we need to consider our suffix is either this, SP, or it's this whole thing. That's a possibility. So that means that in addition, we also need to compute the totals. So in order to be able to avoid computing best across, we actually need to return the total as well. So we need the TAs and TBs from here. And then, this is going to be strengthened to return TA plus TB. Okay, so now this algorithm, basically, it's a bit messy because it has to keep track of all these different sums, but it has the same structure. Divide, conquer, in parallel, just a bunch of sums and maxes. So that reduces this order n to order 1. And then we get work is now linear, and span is log n. Why did I think it was log square n? It's weird. Yeah, I don't think I need log square n. Span is log n. Good. So that's perhaps a more intuitive algorithm, maybe, but it requires some accounting. So linear work, log n span. Exactly what we wanted. Good. Questions? Who feels comfortable with these two algorithms? Raise your hands. Okay, not bad. Okay, for those of you who might have gone lost or something, that's normal. It's look at the notes and you'll catch up quickly. Okay, any questions? All right, so in the next lecture, Guy will talk about graph algorithms and specifically breadth first search by basically building on the same primitives. We're going to show you that, again, like a weakness that you might often hear is that, like purely functional programming is great, but it doesn't work on graphs or whatever, right? That's not necessarily a valid criticism. You'll see that basically all these primitives that we've seen works for various graph algorithms, and in the next lecture we're going to talk about breadth first search. Okay, we'll see you. Thank you for your attention.